Now, in this tutorial, we're going to discuss the angular quantities, and this does not apply for a particle, but actually for a set of particles that are moving at the same time. So imagine there is a body which is composed by a lot of particles. It could be, for instance, a disk or any given body which has a lot of particles. Let's suppose we start with a disk which has a center, and it is an infinite number of it has an infinite number of particles, and of course this center has a radius. And if I analyze, for instance, a particle here, it will have this motion. But if I analyze, for instance, a particle here, it will have all this motion. So you might actually think, well, the trajectory that the outer particle is doing, its trajectory is larger, and of course it is. That is called, for instance, the arc. We're going to discuss about that a little bit later. But both of them have to start and end up at the very same time in the very same place. So the outer particle has to go faster. Now, since we're not going to analyze particle by particle, there is a convenient way of analyzing this, and this is called the angular quantities. Instead of seeing the straight trajectory, we're going to be analyzing the angle, and we call theta the angle displacement, angular displacement. This angular displacement stays, if I start at time 0 here, we can call that 0. And then at certain time I end up in another place. Both of, or all of the particles will perform the same angle. For instance, it could be p radians, or in this case, this goes from 0 towards p half radians. Both of them, or all of them, are going to be covering p half of radians in a certain time. That's called an angular displacement. Of course, the change of the angular displacement due to time is called, it's denoted by the letter omega, and this is called the angular velocity. We are very certain that this will cover 2p radians, or a complete revolution, in one period. So if omega is constant, then we can actually state that omega is equal to the angular displacement, which is 2p radians, in one period. Or in other words, the period equals 2p over omega, and of course, since the frequency is inverse, frequency is omega over 2p. There are usually the angular velocity is also called the angular frequency. Of course, then if there is a change of the angular velocity due to time, this is denoted by the letter alpha, and this is an angular acceleration. So in this case, we're analyzing how the angle is changing due to time, for instance, and we generate angular quantities. You might get familiar with the next expression, because if alpha is constant, then we generate 4 equations of motion, and are the same equations we have been working with previously. The first one is displacement equals initial displacement plus initial velocity times time plus 1/2 of acceleration times time to the square, which we have already used when we were working with a straight line. The velocity also changes in time, and is also initial velocity plus acceleration times time. And the two of them, the rest of them, we have worked with them as well. These other 2 expressions will also be familiar to you. So once again, if we analyze the disk, you might actually see that although the angular displacement of both particles that we are analyzing in the disk is the same, their linear displacement is not the same. So outer particles will displace or have linear displacement which are larger, and we can relate them. We can state that the farther it is from the center of the trajectory, it's higher. So if we call, for instance, this radius 1, and this guy we call it radius 2, the linear displacement or the arc that is going to be generated is denoted with the letter S, is going to be equal to the radius times the angular displacement. And this might be familiar because if we generate, for instance, the arc for a complete revolution, that's the perimeter of the circle, and it's 2p radians times r, and this is a perimeter. Of course, there is a relationship with the tangential velocity, and this relationship is that the velocity is going to be equal to the radius times the angular velocity. And of course, there is also a relationship with the tangential acceleration. And this is, of course, that the acceleration tangential, for instance, equals the radius times the angular acceleration. And of course, if there is this relationship, you might actually remember from a previous tutorial that the acceleration equals tangential to the square plus centripetal to the square root of that. And in that sense, well, we can generate new expressions where the tangential acceleration equals r times alpha, while the radial acceleration is, for instance, velocity to the square over radius, which is radius omega to the square over radius, and this is, for instance, radius times omega squared. And in that sense, then the total acceleration is going to be r alpha to the square plus r omega to the square root of that. I am missing a square here, and this is going to be, for instance, r square alpha squared plus r square omega to the fourth square root of that, factorizing r and getting out the square root of the r square gives me r alpha to the square plus omega to the fourth. And this is, for instance, the total acceleration, not the tangential, right? The total acceleration of any given, that is going to be once again I'm doing that is going to be in the circular trajectory.